Thank you very much. First, I want to give you some impressions today about our project ODE and how we use ontologies for the material data management in metal additive manufacturing domain. The project will still be ongoing for more than a half year, so we'll have time to expand our system more and more. And it's in cooperation with MFPA Weimar, TU Hamburg, and TU Ilmenau. And yeah, today I want to also show some personal experiences and also some learnings, because this was also wished by the PMD in some sessions before. So let's directly dive in. Where's my mouse? Here it is. Why do we actually use metal additive manufacturing? We use it for several reasons. For example, we have design freedom, so we can manufacture complex shapes like this lattice structure here. We don't need any tools for the manufacturing. We can integrate different functions, like, for example, directly printing sensors into the parts, and many more reasons why to use it. On the other side, we have challenges. And one big challenge is that the part and material characteristics are highly dependent upon the processing and the raw materials used. So in order to understand these relations, we actually need a lot of structured data. But in practice, we have along the manufacturing chain a lot of different data sources and data formats. And this results in data silos. And if you sum up all this together, you will find that the people always do trial and error approaches in order to optimize their processes and their part qualities, which is actually very expensive and material intensive. And this is not just in academic environment. So I can see it here in the institute or at the university. We have a project, we do a lot of testing, then the final report is done and all of the data are captured in a spreadsheet in some directory. And 2 years later, you don't know anymore how these data have been generated. But you can also find it in industry. So I've been more than a year at the manufacturer and designer of the PBF-LB machines and at the company which actually manufacture power plants. And you also can find this problem there with their additive manufacturing. So it's not only an academic problem. In order to address this challenge, we actually propose the following system. We can see here an excerpt of the manufacturing chain, starting with the raw material and ending with the actual material characterization. And we want to have an ontology, which is actually just a formal model, which is capable of taking all the information and data along the process chain and structure it in this expandable and reusable model. We also want to be capable of tracking the manufacturing history for each specific part, because, for example, also in academia, you always get specimens which often are numbered just with 1, 2, 3, and so on, and nobody knows where does it come from, where does it have to go. So we want to have a digital part record. And also we want to import these data and query the data in a quite comfortable way using a web interface. This has also come out of this. I created the ontologies and then went to the industry partners, and then they say, okay, congratulations, but what can I do with it? And I think it's a good point, because in order to actually get into a productive environment, we have to embed the ontologies into software which enables users who are not familiar with this technology to interact with it. So what was the actual methodology? How to create the first prototype for such a system? Let's start with the ontology. We have several steps here, starting with the experimental setup. So we have 3 different additive manufacturing processes. First one here at the institute is the PBF-LB process, where you have metal powder, which then gets molten up using a laser. At TU Ilmenau, we have the DADAC process where you have just a wire which gets molten up. And at MFPR, you have the CEM process where you have a mixture between polymer and metallic granulate, and this gets then extruded. Today, I will just focus on the PBF-LBM process because also the web application mainly runs with this process data. So in order to have data, or to have data where we actually can test and build around our model, we did a big experimental campaign. We manufactured in total 450 specimens out of steel and aluminum. You can see here on the right 2 images. These are aluminum parts, how they get out of the machine. And yeah, we did a lot of testing. So basic testing like density, then thermal property characterization, like for example, the specific heat capacity, and then the mechanical testing for impact, compression, tensile, and fatigue behavior. So this is our database. We now know where we actually get the data from. Now we had to define where do we actually start collecting data and where do we end with it. So therefore, we defined our system boundaries. In this case, we started collecting information if the raw material in form of powder is delivered, and we end if the material and the part qualities are gathered. Then you also have to define what questions should actually be answerable using the ontology. Just 2 examples for that. So a constructor may ask for mechanical properties like a tensile strength of a part manufactured using this manufacturing process, or a manufacturer, so a process engineer who is actually doing the settings at the machine may ask how does the density, for example, change if I change a specific parameter like the laser power at my machine. Some thoughts about that. So I think the definition where to start and where to end collecting data is very crucial, because otherwise you will be challenged by asking yourself, okay, which information do I still have to integrate into my ontology? And also the same for the competency questions. There, I think it's always a trade-off between formulating very detailed or open competency questions. So if you have very detailed competency questions, it acts actually like a clear guideline, and you exactly know I need this material property. If you formulate it more open, you actually can avoid to have blinkers and to maybe miss an important factor along your process chain. So I think it's always a trade-off. And next time better, I think it is important to prioritize the competency questions, because it may arise the problem that you don't get information or data that you actually expected to answer a competency questions, and then you have to decide, okay, do we just drop it, or does it have such a high priority that we need to get this information just somewhere else? And I think it's also better to do it in a more iterative way during the whole process of modeling, during the process, to always control, check, and expand the competency questions if it still does make sense according to the current status. So we now know where to look for data and what should be answered. Now we have to go into the actual domain, so the domain analysis. If you talk to the process experts, you will find that every expert uses quite an own language, because of course they are experts on their field, and we want to have these terms in the ontology. So we did a lot of interviews with the domain experts in order to capture these terms. So it followed always the same pattern, asking what are actually the processes in your field. For example, the powder bed fusion process, what goes into this process and what comes out. For example, the powder goes in, the component comes out. What are the characteristics of these in and outputs? For example, the powder has a particle size distribution and the component has a tensile strength. and then asking, okay, where do these in and outputs come from, and where do they go? And this is an iterative approach. So now we have new processes, powder sieving and tensile testing. Then you have to go to the experts for these processes and also capturing the terms. Out of this, we got a glossary with about 200 terms where we actually can have a look at it. This is how it looks. So it's always the term, unit, definition, and then the source of definition. If it was possible, we used standard definitions from ISO or ASTM. And so you will find here, for example, the different processes. You will find the objects, like, for example, the machine, or qualities like the Hall flow rate of the powder. And at the bottom, we have all the different parameters used at the machine itself. So coming back, some thoughts about that. So first, I was struggling a little bit with the definitions, because always asking the question, is it okay to just use a Wikipedia definition? I think yes, at least for the beginning. Then you always can ask your process expert if it is okay. Of course, it is the best way to use standard definitions, but if it's not available, according to my opinion, it is also totally fine to use just Wikipedia. Then it's kind of a trockene Angelegenheit. So you just have this file and you do the interview. So it's a just hard way to define all this stuff. So actually I also try to use concept boards there, but then people just love to work with spreadsheets. Then you get spreadsheets again. So it's also not the best way. And yeah, I think it's just, we have to accept that it's time consuming and you have a high dependency upon the input of your experts. So one challenge that I see is that the glossary acts as a silo itself. So you create it. Of course, you can put it in a cloud and work on it collaboratively, but it feels actually not satisfying. So if you know any tools or methods which could be better in order to create such a glossary or to capture all this terms and definitions, I would be quite happy to hear from you. So now we have the terms and the definitions. Now we need to go one step deeper into the data source and flow analysis. So we have to specifically know what comes out of the machine and what are the data types. Where do we actually find the information that we want to capture? So two examples here. The x-coordinate of the part on the build platform should be later on in the ontology. The source of information is the software where we actually define the position of the part, and the source type is just the OpenJZ file. So it's the build job file which comes out of this software. And you can't find this information somewhere else. You can just find it in this source. Another example, the part material. We want to know out of which material a part is manufactured. So two exemplary sources are the powder data sheet, which is of type PDF, or the process expert may have a look at the part, or he may have seen the powder data sheet before, and he can say, okay, this is aluminum or this is steel. We also implemented a lot of rules in order to use the reason and the inference. So to infer information out of existing information. So for example, for the material type, there's the rule, if you have a powder which is out of steel, for example, and the powder goes into the machine, also all parts which come out of this machine must consist out of this steel. And in this way, we actually defined the rules. So there we use actually two approaches. First one is just in the triple store to define rules, and the other one is a Python-based approach. So we can have a look at some exemplary data sources just to get a feeling. So for example, this is the spreadsheet which comes out of the machine for measuring the particle size distribution of the powder, and later on we can directly import such a spreadsheet. Or for example, comparable, this is the file which comes out of the DSC, so measuring the specific heat capacity and the temperature. You always have this header, but it can also be imported directly using the web application. Or for example, here it's the powder data sheet as a PDF file, and I thought, okay, nice, I can parse this, but then yeah, it's actually a scan, and yeah, I will come to this in a minute again. And I told that we implemented rules. So one possibility that we use is our so-called PI files. So they are used in the triple store that we use, and there you define your rules. So it's always if this, then this, if this, then this. And there are predefined rules, for example, the ODE-based ones for transitivity or inverse relations, and then the rules defined by our own. So for example, say material type, maybe I can zoom in. No, if if you have a powder which is made out of a material and the powder is input of an act of additive manufacturing, and this additive manufacturing process has as an output an artifact, the powder has the same material type as this artifact which comes out of the machine. And in this pattern, you can just define your rules. And the other approach is to use Python, because in this way you can't actually create new instances. You can just create relations. And using Python, you can create instances. So you query using a Sparkle query the instances, then you do your conditions, and then you can also create new instances. Coming back again to some thoughts about that. So it's quite interesting. So most of the data formats are just spreadsheets. Everybody loves spreadsheets, and yeah, it's actually not bad because you can parse them, so that's fine. We had some versioning issues, for example, with the build shop file. In one version, you can find part IDs. In the next version, you can't find part IDs. So we always have to ensure that in the web application, both types are supported. And it's always a trade-off between the work which is necessary to automatically import a data format, or to just create, for example, also a spreadsheet where the user can type in the information. So for example, of course, I can create an algorithm which takes the image, the scan of the powder data sheet, and extracts the information, but this is just much work. And if the powder data sheet changes, we still have to ensure that the properties which get extracted out of it are correct, because we want to have a correct database. So it's always a trade-off. And next time better, I think you need quite a lot of time before the actual manufacturing. If you start at the beginning, in order to do all the interviews, to know what are the actual data types, because if the manufacturing is already done, it's too late if you miss some information. And always this trade-off between, do I create an importer, for example, for this specific machine file, or do I want to generate an one-for-all solution? Actually, I tend to use the specialized solution, because also in productive environments, people don't have time to fill out complex forms. They just are at all capable, according to time, to pick a file and upload it. So actually I focus more on specialized solutions, because you can afterwards also go one step higher. So we now know which data types we have and which information we want to capture. Now we have to think about how we want to model it. So the plan is actually, we have the terms in the glossary. At first, we have to create a taxonomy, so a class hierarchy. In our case, we use the web ontology language, and we use the BFO as a top-level ontology and the common core ontologies as a mid-level ontology. For people who are not familiar with that, you use top and mid-level ontologies in order to reuse existing classes. So you just save some time. You ensure that you can share your ontologies more easily because you used already existing classes. And it also tries to ensure that you build up a consistent model, because the more complex your process and your objects get, the more difficult is the modeling, because you come to philosophical questions like what is time and what is space. And the people have thought about that a long time and just give you their classes, you can use them, and then it's fine. So as already said, the BFO is the top-level ontology, then the common core ontologies, then some specific domain ontologies of Fraunhofer IGCV, which are used for several projects. And at the bottom, we have the actual application ontologies consisting or containing the actual measurement data on instance level. So we took the glossary and created the actual taxonomy. For the initial creation, we used a graphical approach to think about how we want to model it. So for example, here in blue, you have the classes of the BFO, very abstract, so classes like process or, for example, object. Then more detailed classes like act of manufacturing in the common core ontologies or a portion of material. And then more detailed classes like, for example, act of powder bed fusion, then different material types, or here, for example, the different process parameters that are used. And so this is how you start, and then you actually have to implement it to the ontology, and therefore we actually just use Protégé, good old Protégé. I think it's used then since thousands of years, but it has its bugs, but for creating classes, it's just fine. Some thoughts about that, BFO and common core ontologies. So it's hard to understand their modeling, at least for me it was. So BFO comes with a book which has about 200 pages where they explain how to use their ontology, and you have to invest a lot of time to understand their modeling because you have a semantic complexity. So as an outsider, I think it's hard to understand what is actually a contingent or an occurrent because you're not familiar with all these terms. Then you have kind of heavy patterns or redundancies. So for example, according to common core ontologies, you have always the same patterns. You have a quality, then you have the information about this quality, and then you have the place where this information is stored. Also, if you actually are not interested to model all, for example, the place where it is stored, you actually have to follow this pattern. There are also some other approaches, but actually you have to follow it. So you have a lot of redundancies. And I'm always asking myself, do I actually follow the correct modeling? So there are Google discussion groups and stuff like this. And of course, you can discuss with the experts or the colleagues, what do they think about it? But there's still the feeling there may be some mistakes according to the guidelines of BFO and common core ontologies. On the other side, it actually tries to create a consistent modeling. As I said already, you can reuse the classes, so you can save time here. And it actually also guides you during the information acquisition because, I just call it BFO thinking. It helps to categorize the world. So you actually see the world through the BFO eyes, which is kind of a brainwashing maybe, but I think there are worse brainwashing methods, and it's expandable. So this is also quite nice. Queryability, just put it in the middle, because on the one side, it's hard because you have this semantic complexity. So you have to be familiar with the modeling of the BFO. But on the other side, as you have always the same patterns, it's easy to query the information that you need. So it's just not positive, not negative. And yeah, actually I plan to use it for further projects due to the positive aspects, and just add a semantic meta model to use simplified terms also for users which are not familiar with the modeling. We have now the taxonomy, and now we want to use the classes and relations to just model the information, for example, a powder size distribution. And also here you have to think about and draw it in order to discuss. Just to get a feeling, we just draw our patterns. For example, this is how we model an active powder bed fusion. So you have the process as an input, you have an STL model, it has qualities like a volume, you have the information for this volume, you have the place where it is stored, and then the actual value and the unit. So we just draw it in order to be able to implement later on the importers, so the Python scripts where we actually apply this modeling. We will find this later on. So we know how to model now. Some words to the digital part record. So this was the methodology to create the ontology setup. Digital part record coming now. The objective is to link the physical part to a node in the ontology, which is then the digital representation. And to do this, we actually started using unique IDs and QR codes. How these QR codes are generated, I will show later, but you actually have two possibilities to use it. If you are online and you have an VPN access, you get directly to the web application and can see then the manufacturing history. If you are just offline, you scan it, and then you will find information like, for example, the build shop ID, the name of this specimen, and of course also the concrete or specific ID of this part. I will come back to this later on, how to work with it. So we have the modeling, we have the digital part ID. Now we come to the implementation of the web app. So currently it's running on the Fraunhofer IGCV compute cluster, and you need a user account in order to access it, because of course you can add also a lot of incorrect stuff there, and not all people are nice. So yeah, currently you need a VPN and user account. We can have a look at the current front end. This is how it looks. So you have different buttons here to import or to query data. For example, this here is the place where you can create QR codes or upload an open job file, or for example, density measurements. And here you go to the digital part record, for example, just to get a feeling how it looks. Then we come to the implementation of the backend. So if the user, for example, selects from the front end that he wants to import a spreadsheet, then this request goes to the Python backend, in this case, a Flask application. The Flask application will download all the OL files from a repository. So the BFO, the Common Core ontologies, or the domain ontologies as OL files. Then the backend will parse the spreadsheet and actually pick out the information. Then the instances are created using already two. So here we actually use then the blueprint, how we want to model our information. Then the raw data are uploaded to the cloud. Currently we just use GitLab, but of course you can use whatever you like. GitLab is cool because of versioning. And then the triples are uploaded to the triple store, where we currently use GraphDB. And then also the updated old files are uploaded again to the cloud, or in this case, GitLab. Actually, I wanted to have a look at the back end, but I think due to time reasons, we will just skip this at this point. But if you have any questions, please ask them. Some thoughts about that. So currently, I have doubled triples because the triples are in the old files, because I can load the old files using already 2, and the triples are in the triple store. The triple store is cool for reasoning, and of course it's a high performance application also for the querying. So this has some issues because, for example, sometimes if the application crashes, the triples may be found in the old file, but not in the triple store, which is not optimum. And also the performance is, of course, worse if compared to if you only have a triple store or only old files. And you currently can't find inferred results in the old files. On the other side, old files are versionable, which is actually pretty cool. And yeah, good old files. So if, for example, a colleague asks, okay, could you just share your ontology? You just pick the file and send it. So this is good, but better next time. I think it's better to have just the class structure in old files. So, and the instances, so the specific measurement data, then go to the triple store, but not to the old files. I think this could be a better approach. Let's see some examples how at first import the data, and then in the next step how to access the data. The import, we have seen that we work with QR codes, and this is how you do it. So you pick your build job file. This file comes out of your slicer, so where you define your geometries, your parameter sets, and all this stuff. You go to the web application, you just choose this file, you click on OK, and then you will get a PDF file which contains QR codes. Each QR code is specifically for one part of this build job. And you will get a spreadsheet which you can download. In the spreadsheet, you will get some summary data more or less and the generated part IDs. Because later on, for example, you can import density measurements by just having one column with the part IDs and second column with the density measurements. So you just can pick the part ID column and copy it. So you don't have to type all the IDs. Now you pick your file and it comes to actual manufacturing. So you put the file to the machine, the parts are printed, and then you have to number your parts using 1, 2, 3, and so on. And you will find these numbers in your build job generation software. The parts get cut off then of the build platform, and now you can choose you can take your QR code PDF and match the QR code to the specimen using just this simple number. So you will find a QR code carrying a 2 here, and you will find the part carrying a 2 here, and then you know you have to put this QR code to this part. And now this part is uniquely identified with this ID. The parts are printed now. If you scan this QR code or search it by the part ID, if you don't have a smartphone, for example, you will be asked if you now want to import this build job file, because now it's clear that the build job has actually been printed and you have generated the QR codes. The build job file is saved on the server, and now you can just push import automatically, and the information like the parameter sets, the coordinates, the information about the STL file, and so on will be added to the ontology. And also the raw data are backupped. So the build job file itself, or for example, the STL files, we will see this also in some minutes. And then you can go further and import additional test data, for example, from TARP test or your particle size distribution and so on. So we can have a look at it now. Let's see. So as I said, this is the front end. So for example, if you want to import your density measurements, you just choose your file here and you upload it. we can have a look now how it actually looks in the ontology. Could somebody please tell me or give a sign if you can see my screen now?
Yes.
Okay, perfect. Because now I'm on the virtual machine where the app is hosted. Thank you very much. So this is the graphical representation of the ontology, or just a small excerpt of it. And for example, here you now can see this is one node which actually represents one part. And this part is identified with an ID. So this is, for example, the ID of this part. Or, for example, you also have another ID, which is just used inside a specific printing process. And now you can find further information for this part. For example, you see it is made out of a material, and you have, for example, the absorbed fracture energy for this material out of an HRP impact test, and the information about this absorbed fracture energy, and here the actual value, for example, in this case 144, and here the unit joule. And here you can see where does this information come from. It comes out of an Excel spreadsheet, which is stored here in the cloud. And this Excel spreadsheet actually carries also further information, which could be expanded here if you would like to. And this is how you can get further information or find further information. For example, the density of this part, or for example, here the printing process, which has been used, and here the powder with the lot number, the hole flow rate, the size, the particle sizes, or on the other side, what can we find here? For example, here, these are the parameters used. This is one specific parameter, and you can see this specific parameter has been used for a lot of printing processes. Or for example, here you can find the node for the STL file, which has been used, and this is the actual place where the raw STL file is saved. So this is how the information for each individual part is stored in the ontology. Now we can come back again and have a look here. So we have imported now the data, so the build-up file, the different measurement results. If you scan now the QR code or search the part by its part ID, you will come to the digital part record, and it summarizes different information just specifically for this part. This is actually just a query to the ontology. So we have a node with the ID, which clearly identifies the part. And now we query in the background the way of this part to in the ontology. So you will also find then that you have to add further information, which can currently not be inferred. So we also can have a look at the digital part record. I hope it works. So currently every wrong click can be deadly, but let's see if it works. So either you can scan the QR code using a smartphone, but then you can't see anything. So I go this way, search, and it's doing something perfect. Then you will find this. So for this specific part with this ID, we can see we already have a powder lot number. We know the type of material, also could add it now. So for example, these are materials which are queried from the ontology currently, and these are actually the labels. So for example, you can find here steel 1.4404 or steel 316L. It actually comes to the same instance or type of material in the ontology, but some people call it like this and some people call it like this, but it doesn't matter what you choose. Then we also see, for example, at part orientation, which is still missing because here I currently have an issue with the reasoning. And there I also have a question, because in GraphDB, I create a rule, then the reasoner does the inference and I get the results. And often I get strange results because either the rule is false or not as planned, or the ontology includes some information which I didn't expect. And then in GraphDB, it's, at least to my knowledge, not possible to get the way or to get an explanation about the inference. In Protégé, this is possible. So I always try to take the old file, go to Protégé, but the reasoner in Protégé is not the same as in GraphDB. So sometimes I get an inconsistency in GraphDB, but not in Protégé. So if you know a way how to explain the way of inference in GraphDB, I would be quite happy to hear. Then, for example, machining process could be added here. These are 3 methods here. Also here, just a query is sent to the backend asking for machine processes and are displayed here. So if I add in the old file another process as a machine process, I will find it also here. And here also one question. In OL, we have the open world assumption. So only because here the information is not included, that this part has currently not been to a machining process, it doesn't mean that this is true. So I'm thinking about just entering a new process, which is called no machining process, but this also feels a little bit strange to say, okay, machine or part is input to no machining process. So also if you have some best practices, it would be nice to hear a few. And here you can see, for example, then some material characterization results for this specific part. Then let's go back to the presentation. Part record, okay, some thoughts about that. So currently I just put a high focus on clarity. Also for the part record, of course, you can add super easily now information that you want to add further, because the whole framework is implemented, and you now, for example, can also add the laser power which has been used for this part and just show it in the digital part record. I have to discuss here with my colleagues and other people what makes sense here. Then fast adding possible. Yeah, and we use a lot of inference here. So for example, if you add the material type, it is added to this specific part, but also to the powder, as I explained earlier. So in this way, we try actually to take over work of the user, that he doesn't have to do it for all parts, but that it gets done automatically. We now have seen how to import the data. Now we want to actually access it. And currently you have 2 possibilities. First one is using a Sparkle query. The positive aspect here is that you can query what you want. So you can use really complex patterns, but of course you have to be familiar with the syntax of Sparkle and also with the modeling. And as I told you earlier, the modeling using BFO is not that simple, so this is quite hard. In another approach, or a first approach, we actually implemented a guided plot generation, so that you just generate the Sparkle query by clicking through drop-downs. So it's not super fancy, but it actually works. And it works as following. In the front end, you will find always 3 drop-down menus, which represent subject, predicate, and object. So if the user, for example, now does for the subject, select the class A or term A, a Sparkle query is sent to the backend with this information. Then a Sparkle query is done and queries all available instances and possibilities for the predicate and the object. SPARQL query is done to the triple store. Triple store gives back the answer. For example, you have, in this case, two object properties available in the ontology and two object classes. And now the user just gets back this information to his dropdowns. And so you only can select paths where you actually have data in the ontology. And we can see now two examples. One competency question, for example, the manufacturer asks the process engineer, how does the density change if I change the laser speed for an PBF-LB manufactured part made out of steel? Then he can just go to the application, have to go back here and go to create plot. Now, on the x-axis, he wants to have the laser speed. On the y-axis, he wants to have the density of the part. So now he starts just picking the parameter here. So laser speed infill, in this case. In the background now, the SPARQL query has been sent and already come back. And now we see that we have these possibilities. So laser speed has been used or prescribes an act. In this case, we want to have just act of powder bed fusion, but of course I also could use here just act. So this is actually the taxonomy that we can see here. And here I put act of powder bed fusion. Then I add another row. This process has as an output a part, so an object or an artifact. It doesn't matter. Then this part is made out of a material. Now, for example, the data for aluminum are missing here. I can select 316L or metal or steel. I put 316L in here. Then add another row. This material has a quality and I want to have the density. So I choose it and I click on create plot. And now he gets his plot. So we have here the laser speed, and now he could see, okay, if the laser speed is too high or too low, the density of the part will decrease. So he would decide, for example, to choose a laser speed between 700 and 900 millimeters per second, maybe. Now he also could change the parameter here, for example, to laser power and recreate the plot. Now the constructor may come and ask, okay, what about the absorbed fracture energy? So you just can change here from density to absorbed fracture energy, and then you can recreate the plot. Takes a moment. Hopefully it works, and it does. So now you have the laser speed and the absorbed fracture energy. So the constructor may see, okay, we have quite a high range of about 180 joule to about 30. You also can see you don't have any data here currently, so you might do further experiments, but here you can see if you do this for years, for example, you will have quite a comprehensive material library, and the manufacturer may choose here, okay, according to the available data, I may choose this parameter here in order to reach a high absorbed fracture energy. So this is how you actually can access the data. And that's how I actually want to come to an end with a summary. So I showed the methodology from experimental setup to the implementation of the web application, and also some, next time better and personal experience factors. The use cases showed how you can import different types of data to the ontology along the process chain, how the digital part record works, and how you can actually query the process settings and the material data. As an outlook, we want to integrate also the further material characterizations. We want to bring it for testing and bug fixing to a productive environment. So first of all, here at the Institute, but also we are in contact with some companies who want to try it. We want to integrate the two other additive manufacturing processes. We want to apply the methodology to further processes, for example, in hybrid digital, apply it to hybrid material manufacturing. And yeah, also for data access, test different methods to access the data, for example, using large language models, and also integrate different data correlation analytics like statistics or machine learning in order to get automatically correlations and not be or not have to select it manually. So that's it from my side. Thank you very much. If you have questions, then please ask.